Hello everyone, myself Anita Haldar. I am from Isenbos National Center for Basic Sciences. I am working here as a postdoc student in Professor Tanushree Shada's Gupta's group. The title of my talk is Prediction of Magnetic Double Peroxide Compound in a Combined ab-initio and Machine Learning Approach. So I'd like to start with a brief introduction of perovskite, especially double perovskite compounds. As we all know that the perovskite having formula AbO3, where A is generally rare earth or alkaline earth element, B is transition metal, and the ideal structure is shown here, where B forms BO6 octahedra and A cation sits in the void space. Now, if we double the unit cell, then it will be A2B2O6. If we replace one transition metal B by another transition metal B prime, then the formula will be A2BB prime O6, which is the formula for a double perovskite. The ideal structure of double perovskite shown here. Here, BO6 and B prime O6 octahedra, they are alternately arranged in all direction and they are corner shaped. This kind of arrangement is called rock salt ordering. In double perovskite, the presence of two transition metals makes them more tunable and richness in property compared to simple perovskite. These compounds have attracted enormous attention due to diversity of their application, especially the observation of large magnetoresistive effect at low magnetic field with a fairly high ferromagnetic transition temperature in SR2FeMO6 brought this family of compound in the forefront of activity and opens up the possibility to design spintronics material operating at room temperature. In this slide, I'll discuss the present scenario of double perovskite compounds and also the future scope of study. This picture has been taken from this review by Samir Vasala, where they have listed all existing double perovskite compounds. As you can see, the green boxes are the compounds which are stable in double perovskite structure. The red boxes are the compounds, although they have the same composition like double perovskite, but they are not stable in double perovskite structure, so we can call them as not double perovskite. Apart from that, there are many white or empty boxes, and these are the compositions which are yet to be synthesized and studied. And as you can see that there are many combinations like that. So we can say that from double perovskite family, one can have a chance to predict and design new materials with targeted property. Now, in double perovskite, there is a special combination where one of the transition metal is from 3D and another transition metal is from 4D or 5D. This combination is of special interest because most of them are magnetic and exhibit high transition temperature. As you can see from this figure also that their transition temperature varying from 200 to 800 Kelvin. Now, in our case, as we are interested in magnetic double perovskite compounds, so we have considered our exploration set in that particular combination. Now, material prediction in traditional way is a tedious job. It consists of various discrete steps, as you can see, and that's why it's very time consuming and inefficient. So what is the alternative way? Alternative way is used to machine learning on the existing database, and it can accelerate new material prediction. In our case, we have predicted new double perovskite compounds, and this is the schematic diagram of the steps we have adopted in our study, which I'm going to explain in next few slides. This study has been published in Physical Review Materials, and this is the corresponding reference. So in any machine learning model, the first step is to construct the database, which consists of instances, attributes, and target property. Instances are nothing but the existing compounds which we have collected from different databases. Next, the attribute. The selection of attributes is very crucial. We have considered the attributes for which any further computation is not required. Our attribute consists of both structural and chemical information of the compounds. Next is the target property. We have considered the whole problem as a classification problem, and hence the compounds are classified into two categories. One is double perovskite, DP, and another is not double perovskite, that is not DP. The next step is data pre-processing. So we have normalized our data and we have eliminated the outliers. We have also calculated the correlation between different attributes using the heat map, as you can see here. And we set a cutoff and we found that these three sets of attributes, they are highly correlated. So we have discarded one from each pair, and these are the final 10 attributes. So this is the final attribute set. We consider this set for our model construction. So the next step is model construction, which is the most crucial step here. And we have considered trees algorithm for this particular problem. So this is basically based on the divide and conquer method, where root node can produce intermediate nodes on the basis of information gain. And in this process, one can actually reach to the leaf node where all the instances should belong to the same category. We have considered different trees algorithm like trees J48, random forest, random tree, and red tree. And we found that random forest, for random forest, the accuracy is the best. So we consider random forest for our further prediction. Apart from that, we have seen that our data set also suffers from class imbalance problem, as the number of not double perovskite compounds is way more lesser than the double perovskite compounds. So we have treated this problem within cost-sensitive algorithm. The next step is the prediction of new compounds, and this is the summary of our predicted compounds. Uh, uh, as I have already mentioned that we are interested in the prediction of magnetic double peroxide compounds. So we consider B from 3D and B prime for either 4D and 5D. And let me just explain the color convention. These three set for the three different A cations, calcium, strontium, and barium respectively. And the yellow boxes are the compounds which are already there in literature. The deep green compounds, the deep green compositions are the compounds which are predicted strongly as DP according to our model. Then the light green compounds are predicted with moderate confidence. The cross, these compositions are predicted as not double perovskite. And there are some question marks. So for them, the prediction is unresolved. So we have predicted 33 new compounds, but as they are experimentally not known, so we don't have any idea about their crystal structure. So to calculate their electronic and magnetic structure in the next step, we need their crystal structure. So we perform genetic algorithm for that purpose. I'm not going into details for the time constraint. I just want to mention that we have restricted our search space, initial search space in this particular space group where the double perovskites are generally found to be formed, and this actually helps to convert the algorithm way more faster. In the next step, we have validated our result from genetic algorithm in terms of a known double perovskite compound. And as we can see that the predicted structure is quite similar to the reported structure. And thus we got confidence about our adopted method. Then we have used that method to predict the crystal structure of newly predicted 33 compounds. And we found that 8 compounds out of them have highly distorted structure. So we have discarded them. So we are left with 25 compounds. And we have seen that the most of the compounds are stabilized in monoclinic space group, and which is also in good agreement with the tolerance factor. In the next step, we have used density functional theory to study their electronic and magnetic properties. We found that 4 compounds are non-magnetic. So we have predicted 21 new magnetic double perovskite compounds, as you can also see from this table. And we got ferrimagnetic insulator, ferromagnetic half metal, ferromagnetic metal, antiferromagnetic insulator, and one rare example of antiferromagnetic metal. With that, I came to my conclusion slide. We can expect that our study will be a useful guide for future synthesis and experimental study of new magnetic double perovskite compounds, as we have predicted 21 new double perovskite having varying magnetic and electronic properties ranging from ferromagnetic half metals to ferri and antiferromagnetic insulator to ferromagnetic metals, and one rare example of antiferromagnetic metals. Thank you for your kind attention.